Hello, my name is Michelangelo Roger. I'm going to discuss the paper Memory Power Management via Dynamic Voltage and Frequency Scaling. Topics that are going to be covered is going to be abstract, introduction, background, analytical memory power model, performance impact of frequency scaling, evaluation, and conclusions. Let's see the abstract section. So typical server platform memory consumes 90% of the system power on average while running a spec CPU 2006 workload benchmark. While increasing core counts demanding more bandwidth and drive the memory frequency upward, many workloads require much less than peak bandwidth. So this workload suffer minimal performance impact when memory frequency is reduced. When frequency reduced, voltage can be reduced as well. It demonstrates a large opportunity for memory power reduction with a simple control algorithm that adjusts memory voltage and frequency based on memory bandwidth utilization. Evaluate memory DFS, which is dynamic voltage frequency scaling in real systems. Emulating reduced memory frequency. That's the way that they evaluate the paper. On average, we can see that 0.17% slowdown and it shows a 14.4 average, 20.5 maximum memory power reduction, yielding 2.4 average, 5.2 max whole system energy improvement using this method that they propose. Introduction section shows that prior work has focused mostly on CPU energy proportionally adjusting frequency and voltage according to the load. While CPU, DFS, and aggregate power downstairs in various other system components help to achieve scalability, it is observed that the memory system often draws power disproportionate to its load. Current memory systems run at speed that are balanced with respect to the peak computing power, optimized for memory-intensive workload. However, for many other workloads, the performance impact of running at lower memory frequency is minimal. A lower memory frequency allows for lower voltage, furthering power reduction. Propose memory DFS to dynamically adapt the memory system operation point to current needs. So you can see on the figure below that the memory power consumption at high is 80 watts. In the average is 60 watts against the 382 watts maximum of the system, which is the black bar. Background section of memory systems. Subtopic DRAM structure background. So we can see that the set of devices placed together on a DIN comprises a rank. Within a rank, a number of banks consists of independent DRAM storage array, in each device with associated decoders and sense amplifier. So these banks are I/O hardware drivers and receiver, which is part of the I/O hardware, to interface with the DDR bus. You can see on the picture below the DDR bus and the different components. So each bank is a matrix or storage cell organized into rows. The row buffer can hold one active row or page at a time, which an activate command brings a row into the buffer, after which read and write commands can access columns in the row. A precharge command returns the data to the storage array and prepare for the next activation. So we can see various policies go in the way in which memory controller uses these commands. Two common policies are page open and page close policies. The difference is page open keeps the last access row page active in the row buffer. This benefits the performance when the next access is to the same row, because no active is necessary. On the other hand, we have page close perform a page charge as soon as the access is complete. Although this eliminates row hit, it reduces latency upon a row miss, because no precharge is necessary, only an active. Continue the background section on the memory system. So we can see now the DRAM power breakdown on the memory system. Let's start with the DRAM array power. Array power is not dependent on memory frequency. It is asynchronous in operation. Thus, array power is not dependent on memory frequency, only on access count, memory bandwidth. Low power state also have no effect on DRAM array power. Its power consumption is already low when idle. The array draws a constant active state power when read or write or precharge command is active. Let's continue with the I/O power. This component of device power consists of input buffer, read-write latches, DDL, which is delay lookup loop, data bus driver, and control logic, and is consumed when the DRAM is idle, no power down, or active executing command needed. So the I/O power is memory frequency dependent. It reduces with lower frequency. The portion of I/O power due to active command execution scale with bus utilization. This leads to an indirect effect when considering the energy impact of frequency scaling, discussed as below in the figure. I/O power is reduced in memory power down states. Let's continue with the register power. Register power DIMM consists of input-output registers on lock and command address lines. Register power consists of these components as well as associated logic and phase lookup loop. Like I/O power, register power is related to the bus interface, and so it's frequency dependent. It also scales with low power state. And then finally, determination power. Which finally, modern DRAM devices include on-die termination to properly terminate the bus during active operation. So we can see on the figure, we have a comparison between two different frequencies, 1333 MHz and 800 MHz. So you can see when you have lower frequency, you see more energy consumption due to the delay writing or reading on the bus. So each request getting queued, so it take more time to fulfill the request, and then it get more power draw during that time. As this is previously mentioned, voltage scaling have indirect effect of frequency on power down state residences. Because as the memory bus run more slowly, data transfer takes longer. This could reduce the idle time between transfers, eliminating or reducing opportunity to place the DRAM into low power sleep states. Frequency scaling could thus cause average memory power to increase in the worst case. In such case, it would be better to run the bus at higher frequency so that the DRAM can be placed to lower power sleep state sooner. However, it's, it's observed that in many real workloads, there are idle periods between data transfers that are no longer enough to enter a sleep state, even at the highest memory frequency. In this case, slowing the data transfer by reducing frequency with all the times between transfer without reducing the time spent in a sleep state. So as this paper explained at the beginning, they still don't have the hardware that they need to vary the voltage and the frequency at the moment that the paper was reading. So that's the reason they had to create a model to do that effect. So as a baseline, they have the memory power, which is the composed of the power down state active with TCKEHH, faster power down with TCKEL, and self refresh with TCR. So all those three composed equal to 1. So and the memory power is composed of the background and operation power, which you can see on the figure, which is power multiplied by TSR, then power of the CKL multiplied by TCKL plus the CH multiplied by the time CHR. And then you add the power to read plus the power to write, both of them multiplied by the read bandwidth and the write bandwidth. And then you go to the frequency, which is dependent of the I/O power, and you can see that is also taking into consideration the memory power minus the nominal frequency multiplied as well by the memory power, and they get that memory power frequency. Then on the voltage scaling, you can see that is dependent on the first model, which is the base model, minus the frequency scaling model by each power step that they are varying multiplied by the nominal frequency. On the analysis of the performance impact of frequency scaling, we see on the left the figure of the memory bandwidth utilization, how each HP6 2006 benchmark, how they use the bandwidth on different. For example, from left to right, you will see the highest program that use more bandwidth to the lowest program. So on the next feature, we just see the impact of frequency of memory latency. So we can see on the x-axis the bandwidth required, and the y-axis you see the latencies. As you see on different frequency, the lowest frequency, which 800 megahertz, start queuing requests at 4 gigabytes of bandwidth when it start requiring that, and then you see more latency, so requests getting queued faster than, for example, 1333 megahertz that start queuing at 6 gigabytes per second. So you see the impact on frequency scaling based on the bandwidth that is required for that particular workload to run. And then on the figure below, you see the performance degradation, which is program when you get the 800, which is the black, against the 1066 megahertz, which is the white one. So you see more performance degradation on the program that need more bandwidth with lower frequency. Next, on the evaluation section, we have to remember that they are emulating the voltage and frequency scaling and getting here hardware and putting those parameters based on the formulation that we gave before. So on the left picture, top to bottom, we can see the performance degradation that the workload is going to get. So we see that the bandwidth that is more required on the first workload, you see that performance degradation is higher than on the lower side, that you see that the program that doesn't require too much bandwidth, it doesn't get too much performance degradation. Then following the picture below, on the middle you see the power reduction, which you can see that the first workload doesn't get too much of the benefit, but then the subsequent workload, the one at the end, you will see the benefit because they don't need too much bandwidth. So if you reduce the bandwidth, you will get power reduction as well. Then the energy reduction, which is the figure below, you see that first runs it get impacted. There's not much of any reduction. You will see more energy consumption the other way around due to they queue the request and then they have to wait more to complete the process. So then you get more power consumption. But on the other side, you see that the one that doesn't require too much bandwidth, you get energy reduction, and you see a benefit over there. Then on the picture on the right, you will see the program basis of the bandwidth formulation that they have before. Bandwidth is 0 and 0.1, and you see the other bandwidth is 0.5 and 2, how they vary against the. Next, the evaluation that they did was a two program, BZIP and GCC were an intensive program which use memory a lot. So they do a frequency switching behavior. On the top you see how they need different frequency at different moments in time, depends on the bandwidth that they were consuming. And you see when you have a higher bandwidth, they have higher frequency, and on both have the kind of the same behavior. On the conclusion section, we can see that this work proposed and evaluate memory voltage frequency scaling in order to reduce memory power and increase energy efficiency. Starting from the observation that a significant portion of memory system power is frequency dependent. It presents a control algorithm that reduces memory frequency while limiting performance impact. The key observation is that the low memory bandwidth utilization, lowering memory frequency, does not significantly affect memory access latency. By observing memory bandwidth utilization, the proposed control algorithm increases memory frequency when utilizing cross the threshold, bounding the performance impact. They conclude that the memory DFS can be an effective energy and efficient technique, especially when memory bandwidth utilization is low. So we can see that they effectively prove the point that when you lowering the frequency and the voltage in certain applications, you can lower the energy consumption without hurting too much the performance. This paper is fundamental for my research since it shows that DFFs can be used in memory and lower the energy and power in different workloads. So I use this for the big data workload in order to lower the energy consumption and maintaining the performance. If you have any question, please write email to mproject.icu.edu and be more than happy to answer your questions. Thanks.